Hello guys, my name is Dipin Vats and today we will see that how to analyze the algorithms. So before we start, I would like to tell about the two more notations that were left from the previous video. Well, these notations were small o and small omega. I would like to start with the small o first, and according to the definition which is given in the PPT, it says that the asymptotic upper bound provided by the small o may not be asymptotically tight. Well, it means that when we remove the sign of small o, then Gn should be strictly greater than Fn, or vice versa, which says that Fn should be strictly smaller than Gn. If you remember in the case of big O, when we remove the sign of big O, then there was a equal to sign with the less than sign, and it says that Fn should be less than or equals to Cgn. But in the case of small o, it is just Fn should be less than Cgn. There is no equal to sign in the case of small o. So that's why we can say that it is not asymptotically tight. For example, 2n is small o of n square because clearly n is less than n square. So this is all about small o. So let's talk about small omega now. Well, it is opposite to small o, and according to the definition, the small omega, according to the definition of the small omega, the asymptotic lower bound provided by the small omega may not be asymptotically tight. Well, it means that when we remove the sign of small omega, then Gn should be strictly smaller than Fn, or vice versa, which says that Fn should be strictly greater than Gn. Well, in the case of big omega, if we remove the sign of big omega, then there was an equal to sign with a greater than sign, and it was like Fn should be greater than or equal to Cgn. But in the case of small omega, it is just Fn should be greater than Cgn. So that's why we can say that it is not asymptotically tight because there is no equal to sign in this two. For example, suppose there is Fn equals to n and Gn equals to n square divided by 2. Then Gn is small omega of Fn because we can see that Gn is strictly greater than Fn. So now let's come to the main topic, that is analysis of algorithm. Well, there are two types of algorithms, iterative and recursive. And the iterative algorithm is the algorithm in which the steps are executed in iteration. Basically, it means when there is a for loop or a while loop inside the algorithm, then it can be called as iterative ones. As you can see that in the example, there is a for loop from I equals to 1 to I equals to n, and inside the loop it performs print hello. Now coming to the recursive one, it is a type of algorithm in which we can say there is a function calling, which means suppose there is a function a of input size n, and inside the condition there is the same function a of the input size n by 2. Then we can say that the same function is calling again and again. These two types of algorithms are different in terms of solving for the time complexity. When we are solving the iterative algorithm, then we count the number of loops or the number of times the loops is executing. And in the case of recursive algorithm, we use recursive equation to find the time taken by the program. So both of them are analysis wise different. So in order to solve the iterative algorithm first, for the time complexity, I will tell you about some classification in which the time complexity is divided. So let's start with the first one, which is order of 1, which means that the time complexity of the algorithm would be 1 if it do not contain either iterative or recursive algo, means there is no loop, no function, or even if there is a loop, but it runs for the constant time, suppose from I equals to 1 to I equals to 100, then also the time complexity will be order of 1. Just a simple statement, just a simple program with some statements. For example, swap a number or a multiplication program or addition program, etc. etc. Now the next classification is order of n, which means the time complexity would be order of n if the function or the loop is running for the n times. For example, suppose there is a for loop which is running from I equals to 1 to I equals to n and executing the statement this many times, which says print hello. So the hello will be printed n times. That's why the time complexity would be order of n. This is only one example. In the coming videos, I will tell you about some more examples so that you can get the better understanding of this topic. Now, let's come to the next classification, which is order of n power c. N power c. Well, you will get this time complexity for the nested loop. To understand this, let's take an example. Suppose there is a for loop from I equals to 1 to I equals to n, and within this loop there is another loop which is from j equals to 1 to j equals to n. Now both these loops are in the nested form, and the first loop is running n time, and as well as the second loop is also running for n times. Then the total time complexity would be n cross n, which is order of n square. As the number of loops increases, the power of n is also increased, which you will see in the coming questions. Now the next classification is order of log n. Well, we will get this time complexity in the case in which suppose there is a for loop from I equals to 1 to I equals to n, but the I is incrementing or decrementing by 2, 3, 4 or any other constant number. Well, you know that normally the incrementation or decrementation is in the linear form, and so that the time complexity in that case will be order of n when the I is increasing with the power of 1 only, with one digit only, then the time complexity would be order of n. But when it is not linear, you can say that the I is increasing or decreasing by 2, 3 or 4 etc., then you will get the time complexity or order of log n. It should be noted that the exact way to write this in this case, that when I is incrementing by 2, then the time complexity would be order of log n base 2, and when the I is incrementing or decrementing by 3, then the time complexity will be order of log n base 3. Well, it depends, and so on. Well, we will see the further examples to understand it better. Now let's look at the last classification, which is order of log n. In this classification, you should keep that in mind that for every cycle there is an incrementation or decrementation in terms of power, or you can say exponentially. Then you will get such an answer. Suppose I is changing in terms of I power 2 or I power 3 etc. Then you will get such time complexity. Right now just keep the concept in mind so that when in the coming videos we do questions related to the time complexity analysis, then you can at least recall that yes, you have learned it before. So in the next video we will see further examples related to the iterative analysis so that you can understand these classification better. Thank you guys for watching. Have a nice day.